Hello everyone, my name is Prashant and today I'm going to talk about how we can debug a CPU issues or a CPU performance issue. So if you guys look at my previous presentation, the basic aim of these presentations is like how we can monitor and optimize the performance of our Linux system. So before we are going to debug about this CPU issue, I think everybody from the system admin background uh, will have a one point clear that running a server is one thing, but running a server that works well is something else. So let's say we have a system which has been default installed, or this is a vendor default installed system, which is like we have used this ISO which is provided by our vendor, maybe CentOS or Red Hat, and we installed it, and all those servers has come with some kind of a default settings, but those default setting is not giving us the optimum performance. And where is the issue lies? Like in a case of a Linux world, it's really difficult to debug all these issues. And like I mentioned in my previous presentation, because the reason these things are difficult, because we need to have a clear diagram or architecture of our environment, how our software and hardware are interact with each other, and we need a different tools to find it out, like where the issue lies. And even if we have the tools in trade in place, like we have a various open source tools, still interpreting the result of those tools is really difficult. And once we have the clear picture in our mind, like this is the result which comes and this is the part which is causing a performance issue for us, or this is the bottleneck, we then have a exact requirement or exact framework or exact stuff, like this is the thing we need to change to optimize our server. So today I'm going to discuss about a tool called Top, and we can see how we can use it to debug a CPU issues, or in more precise way, how can we narrow down our issue. So before going to a Top, let's run this command W, and let's focus on this line, which is a load average for 1 minute, 5 minute and 15 minute. And similar way, if you can run this command uptime, you will see the load average of for 1 minute, 5 minutes and 15 minutes. Let's run this command top, and on the top line you will see this load average for 1 minute, 5 minutes and 15 minutes. So let me start this presentation with one of the script, which is a simple script, and this will create a CPU bound process. So what it will do, this script or this loop will stuck to one of the CPU. So let's run this loop and now run the top command, and you see that this process, which is having a PID 1687, is consuming 100% of CPU. And with top, if we run 1, you will see it will break down the CPU utilization per CPU. Okay, so here if you can see here, one of the CPU is consuming 99.7%, and that utilization in the user space, and the other CPU is completely idle. Okay, and so this task will, like I mentioned before, this task will completely claim one CPU core, and thus causing a workload. Since this is a task that doesn't do any IO and it doesn't have any kind of a waiting time, therefore for such a kind of a task, this kind of a heavy workload this kind of a workload is considered heavy, because if you are going to start another process, and that process will be going to the queued state because of a lack of available resources, because this task completely occupies this CPU, okay, which is the CPU 0. Okay, now let's kill this. Now our CPU is free. Now let me demonstrate one more script, which is like I run the dd command, which is not going to do anything, but just going to copy my hard disk from dev VDA to the dev 0, and this is going to create the IO. So this is a IO intensive task. Okay, so sorry, it's dev SDA. Now let's go back to the top, and again you see that this gd command, which is going to a D state. Okay, So the load average here you are seeing is a combination of two things. The process which are currently running in my system, which you can see here, and the process which are going into a D state. That is the process waiting for some kind of IO. So in the previous example, I show you the CPU intensive task. Now this is the IO intensive task, which is going to copying entirely my hard disk to null device. And this will also take the CPU utilization to means 100%. Okay, means the heavy CPU utilization, or I can say the heavy CPU utilization. But since it involves a lot of IO waiting time, CPU can do something else during this time period. Okay, so the time in which my CPU is waiting for IO to be back from that device, at that moment of time, my CPU can do any other task. So bottom line is, don't draw conclusion too quickly based on your load average. Okay, and so these are two different scenarios where my CPU utilization goes high because of IO bound process, and second case my CPU utilization goes high because of the CPU bound process. Okay, now the one thing I'm going to show you that this W command is showing something called this much. So from where it is getting this output is from our virtual file system. Okay, so here if you can see, it will showing the same thing, the load utilization for 1 minute, 5 minutes and 15 minutes. This shows the number of processes which are currently running in our system. This shows the total number of processes which are currently running in the system, and this is the PID of this. So if you are going to run this, then you will see this 1703 and 1703. So this is the PID of the cat command. Okay, now let's explore top in more. So what are the different fields which we see when we have run this top command? So the first thing which we already see, now let's look at this CPU column, because this is the aim of this presentation. So if you can look at this column, this is the %US, which is the percentage user space utilization. So means if you start any process, this will show in your user space. So in a simpler word, this is the process started by your end user. So if the load average is high user space, that means server is heavily using by the application, and you need to check on the application side. Similar way, percentages represent the kernel side utilization. So this is refers to the whatever the work which is being done in the kernel space. So in case if this is high, this means your kernel is doing some low level activity, and I means there are a lot of tools which you can use, like for example sysrq or kdump to debug these kind of issue, or various kind of tracing tools like system tap or dtrace, which we are going to discuss later. The third one is a nice, which is represented by ni. So generally you have a nice value, and the process can have a priority from -20 to 19, which is the -20 is the highest priority process and 19 is the lowest priority process. So this shows the number of jobs that has been started with this adjusted nice command, which we are going to see later. The fourth one is the ID, which is the idle. So this indicates the amount of time CPU doing nothing, and the high value of this shows that CPU is not busy, as well as the vice versa. If the values is high, if the value is low, that means CPU means that your CPU is doing a lot of stuff. Fifth one is the percentage wait or wait. That is the amount of time CPU waiting for IO, and in the similar way, the high wait time indicate bottleneck with your storage network or with your disk. These two columns HI and SI refers the interrupts, which is your hardware interrupts, and this represents your software interrupt. So interrupt is the one thing which whenever occur, the CPU need to give that task to the immediate attention. And if you need to look at the interrupt in your system, just refer to this or look at my interrupt video. Okay. The last column %st is refer to the case where you are running a virtual system. So %st refer to the stealth. So in case if you are running any virtualization it refers to the amount of time stealed by your virtual machine from your host operating system. So if this is too high, you probably need to check what is going on in your virtual system, or probably need to migrate that VM out of your physical machine. Okay, so this is one thing. The second thing which I missed is like a number of tasks which is currently running on your system. One is which is current 10 total is the total number of tasks which is running in your system. There's a number of running tasks, number of sleeping tasks, stopped, and zombie. Okay, if you want to have more information about it, just refer to man ps, and here you can see the process state codes. Okay, now let's look at the memory section, this one. So I think most of you have always ever run this command free. Okay, so if you run this free -m, you will see almost a similar output like this. Okay, this. So your top command is basically a combination of your W, okay, this uptime, free, and the process in the recursive or in the dynamic state. Okay, so the first column or the first value represent the total, that the total amount of memory which is present in your system, that is the physical memory. The second one represent the use, that is the amount of memory currently in use, including your cache memory as well as your buffer memory. Free is the amount of memory which is free in your system, and you always need to refer to this line to make it how much amount of memory is currently free in your system, which is a combination of this free, buffer plus cache. Because whenever your system runs out of memory, cache is the first place where kernel looks and release the memory. Okay, the fourth column is the buffer memory. So buffer generally consists of your metadata, that is your inode, entries, file system tables, all those things. So if you are really interested in this, just run slaptop or proc/slabinfo and grep -i entries. Okay, or if you need to look at the dynamic output, like we are seeing with this is top command generally represent whatever occurring in the user space. It has, like, for example, these are all the kernel threads. Okay, so if you look at what are exactly this, like for example, we have a lot of column over here, but the main thing which system admin focus and not means these are the main area of focus for the system administrator are this cache size as well as this name. So here if you look at this entry laptop, okay, so current size of entry, and if you need to look at the actual utilization of the kernel, means how much memory is our kernel is utilizing, you can even check it over here. Okay, so it's like 55 MB, which is not much. Generally, if this goes high, it might be a issue or a bug, based on my experience. So whatever I see so far, if this slab goes really high, because this is generally refers to the low level where all your assembly codes works. So generally you don't see, because our kernel is so much stable that you generally don't see issue on the kernel side. But in case if you see that okay, this entry is consuming so much of size, then in that case please refer to the Bugzilla, Red Hat Bugzilla. Okay, now fourth thing is so we have covered total, use, free, buffer. Now let's look at this column called cache. So means instead of reading data from a disk, which is like a 1K times slower than your RAM, data is cached and read from cache for faster accessing. Okay, so this is how it works. So this is your app, which is first going to look inside your RAM, or this is your cache, and ultimately it look to your disk. Okay, for CPU has its own internal cache which is either L1 L2 cache, which is faster. Then it will look for your cache memory and ultimately it will look for your disk. Okay, this is how it works. It's nowadays modern CPU has L1 L2 or L3 cache, and this is the way you can check it. ls CPU command. Okay, the system has L1 L2, or it's a data cache, or it's a data, or I forget about it, what is the other one, but index cache or data cache, or I don't know right now, but this is how you can see it. Okay, now let's look at the other column. So we have something called swap. So the simplest way to explain swap is like it's a emulated RAM, and because it is where it is in your disk, so it's slow. But there's a common misconception that whenever your system is swapping, it's generally refers to like it's a bad thing which is happening, or it's like it's a performance hit. But this is not always true, because in case if system need to move some of the anonymous pages, then in that case the system will swap. So if during the process of freeing up memory, your kernel moves anonymous pages to swap to free up your RAM. But if the kernel is moving data to swap because of memory pressure, then it will cause your performance hit. So there are two different things, whether kernel is moving the anonymous pages or whether kernel is moving your actual pages. So both the cases are different. Okay. Now we have already looked at these columns, like your buffer memory, your cache memory, and there's one thing called shared memory, which is like the pages which is being shared between different processes. So if you run this, you will see there's some of the shared library which has been represented by this, which has been shared between different processes. Okay, so let's go back to our discussion where we are discussing about our buffer memory and cache memory. So there are ways in which we can free this buffer as well as cache. So this is a command which is going to free your proc sys vm drop underscore cache. Okay, but this is never ever recommended in the production system, because your kernel again need to build your cache and it will eventually slow down your entire environment. So the cases where this command is referred is in the case of your test environment. So let's say you are testing some application and you find out that there is some kind of memory leak, and whatever the content which is present in your cache or your RAM is a buggy one. So in that case you can run this, and before that run the sync command. So it will flush all your dirty pages to your disk, and then run this. Now if you check the output of free-m, your buffer and cache are all gone. Okay, so echo-3, this one is going to flush or free your page cache, your entries as well as inode. If you are going to run echo with 1, it's only going to free your page cache, and if you run echo with 2, it's going to free your entries as well as inode. Okay, so let me check if I have this RPM installed. Either share kernel, either share doc, kernel-doc. Okay, no. So I don't know if I have the yum repository installed. Okay, so like I mentioned, please do not run this in your production system. In the meanwhile this is running, let's run the top command again and look for other column. So first one is like self-explanatory, that the PID of a process. Second column is like the user who is running this process. Priority I already explained. Nice is the same one. Then this is word, which is the virtual memory of a process. Okay, so what exactly is this virtual memory? So this is the amount of memory that the process claimed when it is started. Then we have something called res or resident memory, that is the actual memory. So this is the amount of memory which is actually using. So your resident memory is always lesser than as compared to your virtual memory, and because whenever the process starts is over allocates the memory then they actually needs it, and the actual memory which is being used by that process is being mapped, means your virtual memory is mapped to your physical memory, means the resident memory is the actual memory which is being used by your process. So virtually memory is like too much, but if you need to check out like how much is the actual memory which is being used by the process, you always need to focus on your resident memory. So SHI is the shared memory, that is the process, the memory which is being shared between the process. S is the state of a process. Percentage CPU is the refer to the amount of CPU time that the process is using, and generally your top command output is being sorted with the percentage CPU utilization. Same way, if you run shift with -m, the top output will be sorted based on memory, shift with m. And the same way, the percentage m shows the amount of time, the percentage of memory claimed by the process. Time is like for how long this process is running, or the amount of time this process is using CPU cycles. And last one is the actual command which is running. Okay, so this is just a brief introduction to your top command. So just want to demonstrate to you guys like this kernel-doc is one of the most important package, and once it's been installed, you can refer it over here, and it has got the wealth of information. One thing I want to show you guys is drop cache. Okay, so like I told you, this 3 is going to drop your page cache, your entries and inodes. The echo 2 is going to free your entries and inode, and 1 is going to free your page cache. But always be careful and not to run this command in your production environment. Okay, now after looking at this, let's look at one more tool called vmstat, which is also come from the sysstat package family. So if you run this, or sorry, proc CPS family, I'm sorry. Okay, so this has got a lot of stuff like free, pgrep, pkill, like the frequently used command or slap top, which you just run top, uptime, vmstat. Okay, so let's run vmstat on its default mode, which is called the sample mode. So if you run vmstat with this, where we are asking vmstat to poll the system 3 times with a 1 second interval. Okay, so first 2 column, which is run, and second one is a blocked. Okay, so let me tell you something about this, how this process works. So like say if we are running any of the process, so before that process is being served by the CPU, every process enter into something called a run queue, and in the run queue for every CPU maintains a run queue. So, or the other way to say that there is a run queue for every CPU core in the system. So once the process is in run queue, it can be runnable or blocked. Okay, so if it's runnable, it will show in your status or stat as running, or either it is going to destate. Okay, so a runnable process is the one which is competing for CPU time, and kernel need to decide which process it will run based on the CPU time. Okay, so this is how it works. So if this run queue is increased, that means this is a process which is competing for CPU time, and if this process blocked, that is, it is waiting for some kind of a IO. And like I mentioned earlier, this load average is a combination for the process which is in the running state as well as the process in the blocked state. So if your running state process is high, or the CPU load generated by those processes is high, as well as the process is going to a D state because it is waiting for some sort of a IO, or sometime in the case of memory pressure it might go into a D state, then in that case you will see that your load average will shoots up. Okay, now let's look at some other things which will affect your CPU performance, and one thing is called context switches. So we know that nowadays, like most of the system has quad core or 8-core system, and our kernel is a kind of a multitasking, so it means it can need to switch between from one process to another. And to perform a switching from one process to another, it need to save all the context of the old process and retrieve the context information of the new process. And if the system is constantly doing this, then you will see like a huge performance hit, because every time kernel need to flush the context of this, means need to save, flush the context of the old process, and then need to load the new process. So the way you can check it is like pid stat-w command. Okay, so here if you can see like the process and the context switching. Even in vmstat, if you look at this column CS, there is a context switching which is happening. Okay, so if you see the higher value of this context switching, you will see a performance hit, and what is considered to be a higher value will depend upon the environment. Okay, before finishing this presentation, I just want to show you one more thing. CPU info and grab -i processor. So now here we can see that this system has two processors. Now I want to find it out which processor running on my CPU 0 and which processor running on my CPU 1. So for that I have the simple command ps-eo pid argument and psr, which shows the processor currently assigned to this process. So here if you can see that this is assigned to my CPU 0 while this is assigned to 1. Whatever the process which is showing in these boxes is those are the kernel thread. Okay. And if these are the normal user space running process. So here if you can see that this process means, if you are aware of that, like the Apache will fork the 8 thread or the 8 child process when it start. So here if you can see that this same process is assigned to this, while the other child is assigned to the CPU 1. So this is just a little bit introduction how we can debug CPU issues or CPU performance issue, or in the other sense how we can narrow down the CPU performance issue. So thanks for watching this video.